Welcome to Module 2 for UHPC Material Properties. We're pleased to welcome our speaker, David Garber, Interim Chair and Associate Professor in the Department of Civil and Environmental Engineering at Florida International University. David?
Thank you, Mary Lou. All right, and then thank you, Royce, for getting us started today. So today I'm going to be talking about our Module 2 material properties. And I'll start with a brief background on UHPC, which Royce already covered if you were watching during Module 1. We'll talk about the general mix design and a general overview. Again, if you're just hopping on for Module 2, it will be a quick overview. And then the focus of the presentation will be on the typical material tests and results, reinforcement bond testing, and some short discussion on conventional concrete to UHPC bond or cold joints. So UHPC is a cementitious composite material with a high compressive strength, high stiffness, and the defining characteristic is mainly its high tensile strength and sustained post-cracking tensile strength. Typically, we have steel fibers included to provide the high tensile strength and the required post-cracking response. And there are both pre-bagged commercial or proprietary and non-proprietary UHPC mixtures. As Royce mentioned, there are a number of different applications. We look at three of the main categories. They have been mainly used in joints in the past, but also there have been some overlay applications in the US and especially in Europe. And then also we're starting to look at in the US more applications with precast pre-stress elements and also precast deck panels. As Royce mentioned, there are a lot of different definitions for UHPC. He went through these in more detail in the previous presentation, but we have high compressive strength, so high tensile strength, high stiffness, typically a smaller drying shrinkage, higher autogenous shrinkage, and it's a high flow material, so with static flows in the 8 to 10 inch range. There are a number of different definitions. I'm summarizing some of them on the slide, but generally we have minimum compressive strength between 18 and 22 KSI, and some kind of definition for our tensile strength, either measured through direct tension or through a modulus of rupture type test. And on a number of these slides, I'll have information. Again, you can download a copy of the PDF from the handouts, and these will also be in the archives on the ABC UTC website. As Royce mentioned, UHPC materials will include binders and supplemental cementitious materials, fine aggregates, typically like a silica sand or ground quartz, different chemical admixtures, so superplasticizers and high-range water reducers, and sometimes viscosity modifying admixtures can be used to stabilize heavier fibers. Typically fibers are steel, brass coated, and 13 millimeter or half-inch length and 0.2 millimeter diameter. Again, as Royce mentioned, there have been a number of studies throughout the US and around the world on non-proprietary UHPCs. So here's a summary of some of those studies as well, which you can refer back to. So the project here at the ABC UTC, again, it was a collaborative project between FIU, OU, University of Washington, University of Nevada, Reno, and Iowa State. So we had different universities around the US looking at the mix design and seeing how a similar mix performed with local materials from different parts of the US. So our developed mix, we based on the OU mix, and we had our aggregate from Titan here in South Florida was a masonry sand, a limestone masonry sand. We looked at a couple different types of cement, but ended up recommending a type 1-2 cement from Titan again here. Our slag from Argos and Tampa, and superplasticizer and silica fume from BASF, and then our steel fibers that we were recommending at the end were just the typical half-inch fibers produced by Hyperfiber here in the US. The compressive strengths that we saw were around 17 or 18 KSI to 20 or so without any heat curing. And we did modulus of rupture tests and found with the final mixes a first crack above 1.5 and the peak above 3. So similar to what Dr. Floyd mentioned, we looked at the particle size distribution for our constituent materials. We had similar constituent materials to what Dr. Floyd mentioned, and then we also looked at our local aggregate provider also has a ultra fine recovery material, which was finer than our sand, and we looked at including that in different proportions as some of our fine aggregates to get a better particle size distribution that better matched the ideal curve. We also looked at several different types of fibers here at FIU. We looked at the two types of the typical brass-coated half-inch fiber, so one from Beckhardt and one from Hyperfiber. Then we looked at a half-inch fiber with a little larger diameter from Helix, and then a larger length fiber, but with a similar aspect ratio, again from Beckhardt with hooked ends. And then we also looked at another fiber here, the synthetic fiber from GCP. So you can see it had a lower strength and a higher aspect ratio. And in general, I wanted to highlight, as Dr. Floyd mentioned, it's important to have a high tensile strength for these fibers so that the fiber slips in the matrix before rupturing. And this slip gives the UHPC some ductility. So the mix that we ended up recommending as the final mix, you can see some of the cost breakdown. It ended up being around $800 per cubic yard. So this is, and most of that cost is from the cost of the fibers. So this is significantly less than the proprietary mixes. So this was one of the main advantages of using a non-proprietary mix. At FIU, we mainly did material tests. So we did some small batch mixes using just a bread mixer. So 115 different mixes here, looking at the flowability and the compressive strength. And then we did 10 larger batches using the vertical shaft mixer that Dr. Floyd mentioned with a 2.2 cubic foot capacity, where we did more material tests there. So for initially working on a trial batch, the little bread mixer is easy to use, and you get about 6 3 by 6 inch cylinders. So this can be a place to start if you're just playing around with it for the first time. And then these vertical shaft mixers, can be rented, or they're not too expensive, so you could get them for the larger mixes. So with UHPC, now I'll start talking about some of the different material tests. So in terms of standardized tests, there's an ASTM C1856 that's specific for UHPC materials. And this ASTM standard basically refers you to other ASTM standards with slight modifications for UHPCs. So, referring to for compressive strength, C39, but we're using a smaller cylinder, so 3 inch by 6 inch cylinder. And as Dr. Floyd mentioned, a higher load rate. So when they give some other definitions for flexural strength, modulus of elasticity and Poisson's ratio, creeping compression, and then length change or shrinkage. And as I had mentioned, the tensile strength is what really makes UHPC. But before July, there wasn't a standardized method for testing the tensile strength of UHPC. So there have been different methods that have been used by individual researchers using various shapes. So some researchers have used dog bone shapes, some prismatics of 1 inch by 1 inch size or 2 inch by 2 inch sizes, and different test protocols. So most of the researchers would define their test protocols, but it wasn't standardized in the past. So the direct tension test developed by Dr. Graybill and FHWA, they initially published the work back in 2013, but just recently in July, they standardized it through AASHTO. So AASHTO test T397-22. So Dr. Grable will talk about it more, but it's a 2-inch by 2-inch prism that's loaded in direct tension, and you need to measure some different properties for it. You can also measure the tensile strength using split cylinder and also a double punch test, and then also a modulus of rupture test, which was on the previous slide. So recent work by researchers at the University of Florida found good correlation between the maximum bending and maximum direct tension, and then also the maximum double punch and maximum tension. So the double punch is kind of like a cylinder where you put a little steel cylinder on the top and load it until you get a split here. And there's good correlation between the ultimate tensile strength of that and the direct tension. So here is the typical tension behavior. Will be about linear elastic up until we have first cracking. We'll have a slight drop in strength as the fibers become engaged as you have the crack in the cementitious matrix, and then a increase in strength, and that's sustained post-cracking ductility. The area under the curve is the toughness provided by that UHPC. All right, so now I'm going to shift gears and start talking a little bit about the test results that we had with our mixes, and then also I'll tie in some of the results from Dr. Floyd and the mixes that they looked at OU. So first, looking at the flowability, we found that the fiber type didn't affect our flow, but an increased fiber content decreased our flow. We also saw that when we decreased our water to cement ratio, we decreased the flow. And when we used that ultra fine recovery material, it increased our high range water reducer demand. But in all cases, by modifying the high range water reducer a little bit, we were able to stay between desired 8 and 10-inch flows. So here are some results from OU. So they found that when they increased the fiber content above 4%, so for 4 and 6%, they saw a decrease in the flow, even when they increased the high range water reducer. So here for the 6% fibers, they increased the high range water reducer, but they still were only able to get about 4-inch flow with for that mix. Here again from the University of Oklahoma, they found that the set time increased with the high range water reducer dosage. So here, with 15 ounces per hundredweight, they saw set times less than 6 hours. And then when they increased that high range water reducer, they got the final sets greater than 12 hours. And here again, as they added more fibers, going up to 4 and 6%, they needed more super plasticizer to get the flows that they were looking for. So we looked at the effect of fiber type and content on the set time, and we found in general that when we increased our fiber content, it decreased our set times, and the fiber type didn't have a significant effect on the set time. So here with the increased fiber content up to 4%, we saw the decrease in set time compared to our 2% fibers. Next, we'll look at some of the results of compressive strength and the effect of some different variables on compressive strength. First, we saw that natural moisture content led to a large variability in our results. And so yeah, to start here are 3 of the same mixes with a water to binder ratio of 0.18 and 3 of the exact same mixes with a water to binder ratio of 0.2. They were cast at 3 different times with a natural moisture content aggregate without adjusting the water content or without adjusting the added water based on the moisture content of the aggregate. But you can see there was a large variability in the compressive strength between mixes. So what we did and what most researchers have done is oven dry the fine aggregates to better control the amount of moisture that's in the mix. In terms of cement type, so Dr. Floyd mentioned this a little bit, but with cement type, we looked at 5 different types of cement, and generally we found type 1, 2 to give us good compressive strength, and it was and good working time. We found type 3 to give us a higher strength and higher early strength, but it decreased our working time. In terms of water to binder ratio, we looked at a few different water to binder ratios and found 0.2 to 0.18 to give us the highest strength. After 0.18, with higher or with lower water to binder ratios, we saw a decrease in strength. In terms of our high range water reducer content, when we increased our water reducer, our high range water reducer, we saw a decrease in strength. And I wanted to mention here, this is likely has to do with how the water to binder ratio is calculated. So there are a couple different ways that we can calculate our water to binder ratio. So the first, just water to cement ratio, where we have the weight of the free water plus the weight of the water available as moisture content in the aggregate, divided by just the weight of the cement. So when we add supplementary cementitious materials, we need to also include that in our water to binder ratio. So again, the weight of the free water, weight of the water in our aggregates, divided by the weight of the cement and the weight of our SCMs. With UHPCs, they're more sensitive to the actual water content in the mix. So we should also consider the weight of the liquid portion of the chemical admixture. So this has been done by some researchers. We didn't think to do this until we were analyzing the results at the end. But this is the modified water to binder ratio, where you also consider the weight of the liquid portion of the chemical admixtures. So this is why we think we saw the increase in the high range water reducer decrease our strength. In terms of the fine aggregate type and content, we used an ultra fine recovery material, and when we added this, it allowed us to improve our particle packing in the material and gave us higher strengths. So with a 20 to 30% replacement, we saw an increase in strength. So in terms of the fiber type and content, we saw similar compressive strengths and densities for the mixtures with steel fibers, regardless of the fiber type or content. So you can see the first 5 mixes here. When we used our synthetic fibers, we saw a decrease in the compressive strength, with a larger decrease in the compressive strength with 2% synthetic fibers versus 1%. And also you can see a drop in the density when we were using the synthetic fibers. In terms of the fiber type and content, our steel fibers our steel fiber type and content did not have a significant effect on the modulus, but the OL and HF fibers led to the highest splitting tensile strength, and the synthetic fibers led to a lower modulus and a lower splitting tensile strength. In terms of the flexural strength modulus of rupture, all of our steel fibers led to modulus of rupture strengths over 2.5 KSI. We saw that when we increased the fiber content, so going from 2 to 4% fibers, this increased our rupture strength. And the type A fibers, which were the longer fibers with the hooked ends, they had similar results to our 2% fiber content. And then the synthetic fibers, they had the lowest modulus of rupture strength. So here's some results from University of Oklahoma again. So they looked at different fiber percentages from 0 to 6% with the 3 different ways of finding the tensile strength. And they found that an increased tensile strength occurred when they increased from 0 to 4% fibers. And then they saw a decrease in strength when they went to 6%, likely because of consolidation issues. So here the white column and the filled in column here are from direct tension, so first tensile crack and the post tensile crack. The gray column here is the splitting tensile strength, and then the dark gray column, the flexural strength. In terms of creep, we did not do any creep testing at FIU, but they looked at creep at the University of Oklahoma, and they found that an increased fiber content led to less creep. So here is the creep results for 0%. As they increased the fiber content, the creep decreased. Similar results for shrinkage. As they increased fiber content, it decreased the shrinkage. So here for 0 and 1% fibers, and then 2%, and then down to 6% here. So, and they saw similar shrinkage between 2 and 4% fibers. So we also saw similar shrinkage, measured shrinkage between 2 and 4% fibers. So here, similar with the OL fibers, similar with the hyperfibers as well. So next, we'll look briefly at bond and development of reinforcement. The bond of the reinforcement can be measured through pull-out tests and then also through beam splice or development tests. So a pull-out test is like a cylinder block of concrete with a bar embedded and a bond breaker at the top to reduce the influence of the support on the bond. So they looked at Dr. Floyd and at the University of Oklahoma looked at this type test and then also a splice beam test. And with the splice beam test, they had bars coming with a 2 bar diameter splice length at the middle. So a quick overview of some of their results. And again, this was with the non-proprietary UHPC material. They found that an increased fiber content led to an increased pull-out load. So going from 0 to 6% increased the pull-out load capacity of number 5 bars and number 8 bars. But note that with the geometry, they weren't able to yield any of these bars. So these forces were still under the yield capacity of the bars. So just looking at the pull-out load capacity. Here, looking at the bond strength again, so proprietary UHPC had a larger pull-out load, but if you normalize by the bond area and the compressive strength, then there was a similar normalized bond stress between the two. And then in terms of the beam splice tests, a higher fiber percentage increased the capacity of the beam splice test. So here are some of the results for moment versus midspan deflection. And again, the proprietary mix had a slightly higher strength, but you can see the non-proprietary mix here also performed well. And I wanted to note, so in some applications, such as simple for dead, continuous for live, you may need to splice pre-stressing strands. There's been limited work in this, but Dr. Graybill and FHWA did some testing, and they found that the splicing of pre-stressing strands or in UHPC, the development length decreased to about 16 inches for, or 15.7 inches for half-inch strand, and then 23.6 inches for 6/10 inch strand. And these were straight strand tests. In terms of cold joints, as I mentioned earlier, most of the applications right now are, for UHPCs and non-proprietary UHPCs are in joints. So the joints are typically between conventional concrete precast elements. So the bond strength of UHPC to a precast conventional concrete element is important. And you know, with these tests, you typically want to see the failure not necessarily at the joint, but in the conventional concrete component. So some of the different ways that bond strength is measured is through a slant shear test. So this is like a typical cylinder, half cast with conventional concrete, and then UHPC cast second. This is it's shear with a normal force across the shear plane. You can also test the flexural bond strength using kind of like a modulus of rupture type beam test, where again half is the conventional concrete and half UHPC. So conventional concrete cast and allowed to harden, and then the UHPC cast after. Split cylinder test, half conventional concrete, half UHPC. Direct tension pull-off tests. So with this, a slab of conventional concrete is cast, allowed to harden, and then the UHPC cast on top, and then a cylinder is cut between both materials, and then a tension load applied, and you know, you see the direct tension pull-off strength. And then also a bisurface shear tests are sometimes used. So this is similar to the slant shear, where you're looking at the shear stress of the interface, but you have a normal force across the cold joint. So as Dr. Floyd mentioned, they did some testing with non-proprietary UHPCs, and in general, they found that the best performance for retrofit applications were with sandblasting. And they looked at flexural bond, slant shear, and direct tension pull-off. On this slide and the next slide, I'd summarize some other test results. I'm not going to go through them, but again, you can reference this in the PDF handout. But a significant amount of work has been done looking at the cold joint between conventional concrete and UHPC. So here are some additional studies. In general, with the bond between conventional concrete and UHPC, we have a sufficient bond is typically observed when the failure occurs in the conventional concrete substrate. So when you're doing any of these bond tests, that's typically what you want to see. And then we can generally get good bond between the conventional concrete substrate and the cast in place UHPC material when we provide either a 1/4 inch roughness surface finish or sandblasting for repair applications, and some type of sustained pre-wetting. So like a wet burlap that's left on for 6+ hours, or some type of water ponding. And I also want to mention that generally most researchers and practitioners will just kind of approximate the magnitude through visual inspection of the surface roughness. But there are some more complex methods for measuring the surface roughness. And I reference a paper here where you can see some 3D visualization techniques. So in summary, most UHPC material properties, proprietary and non-proprietary, can be determined using tests that are similar to conventional concrete tests. The one difference is when we're measuring tension, typically, so the flexural strength can be measured similar to conventional concrete, but the direct tension requires a different test method. So this AASHTO T397-22 procedure. And in terms of tension, the post-cracking ductility is as important as the ultimate tensile strength. And in general, we can get sufficient flow and compressive strength and tensile strengths and behavior using non-proprietary UHPC mixes. So with that, I'll conclude the presentation, and I'll be willing to answer any questions.
Thank you, David. We'll now begin the Q&A session. Paul?
David, real good. We have our full 10 minutes pretty much for our question and answers. So we'll go on and get into that. The first one came in beforehand is, how do we quality control the properties of non-proprietary UHPC?
Yep, that's a great question. And I think states are still thinking about this question. And I guess I've heard that it may be twofold, where a contractor or precaster, or one approach would be where a contractor or precaster could, go through and get a mix pre-qualified, using their specific materials, and then there would be some type of, simpler test where they can check the quality of the individual or of each individual mix. So, and I don't know that anything's been finalized with any states yet, but an example would be they would need to do the direct tension test for the initial mix qualification, and then maybe a simpler test, like the double punch or flexural test, in the plant, or when they're seeing how the actual mix that they used performed. So, I mean, some type of a approach like that, I think maybe what ends up, but like I said, again, I'm not exactly sure, but I mean, something like that.
Okay. How would someone actually come up with a UHPC mix design?
Yeah, so I think Dr. Floyd covered this in the previous presentation, but I think the starting point would be looking at all the work that's been done by previous researchers. So getting basic proportions from either our work or the many other research works that have been done throughout the U.S. And then looking at the specific material properties for for your region or your location. So, and then from there, doing the initial, small batches to look at compressive strengths, and then, sizing it up to also look at the tensile strengths.
Okay. We got a few fiber questions here. The first one, this came in new. Was there any fiber dispersion issue during casting for the hook-ended fiber case?
Yes. Yeah. So we had to use for larger fibers. We used viscosity modifying admixtures to. So with the Dre mix fibers, we found that in our mixes, those fibers would settle and clump. So we used viscosity modifying admixtures to kind of stabilize those fibers. And then, yeah, we saw some floating with the lighter fibers as well. So, but with the VMAs, we were able to kind of stabilize the fibers in the matrix.
Okay. One here this is a new one, but have the FRP macrofibers been tested in the mixtures?
We didn't look at any FRP macrofibers, so I'm not sure. Right. I guess the tensile strength is, I think, the most important characteristic of the fiber. So you want a higher tensile strength so that the fiber slips before rupturing. So our synthetic fibers had a lower tensile strength, so we saw lower tensile strengths with those mixes. And what else? Yeah, right. So I think it's, as long as it would have the higher tensile strength, so like 300 to 400 KSI, I think Anyway, but we didn't look at FRP fibers specifically.
Okay. Then here's another one on that. Apparently, there are non-metallic FRP composite macro fibers. I think they have a mini bars trademark, but it can be used to replace steel microfibers. Do you know anything about that?
I don't know anything about those, but it'd be something interesting to look at.
Okay. And here's another question that came in during the talk. Was the UFR a silicon-based material?
The limestone.
Okay.
Yeah, I mean, they essentially just, they dredged out any, it was like a recovery material. So they dredged out any leftover finer aggregates that didn't make it, when they were producing their typical masonry sand.
Okay. Another question that came in beforehand was, what are the allowable size of placements? Was there any restriction on the size of maximum dimensions, setting times, or early strengths and amount and type of fibers?
Sorry, say the so in terms of setting times, yeah. So I mean, our setting times, or Dr. Floyd, when they only used 15 ounces per 100 weight, they saw final sets less than 6 hours, but they got above 12 hours when they used more high range water reducer. So, we were typically the final sets between, 9 and 11 and a half hours.
And what were some of your early strengths?
Right, early strengths, I think 10 plus at 3 days, so 10 to 14.
Okay, and how about the size of placements? Any restrictions on that?
The main restriction on the size of the placement would be your mixer. Our mixer, or our largest mixer here, we could do 2.2 cubic feet with it's a Mortarman vertical shaft mixer. So the horizontal shaft mixers, you can do larger capacities, or they make larger capacity mixers, vertical shaft mixers as well. Right, and I guess typically the stated capacity, for mortars or other materials, when you're mixing UHPCs, the actual capacity you can mix would be significantly less than the capacity of the mixer, stated for mortars or other materials.
Okay.
But, yeah, I think the mixer size would be the main limitation for the size of the placement.
Okay, it's 12:19. I'm going to go ahead and ask Rick if he wants to pick up any questions that came in during the Q&A.
Yeah, so David, there was one quick question here. Why does fiber content influence set time?
Right, and I guess I'm not exactly sure. I mean, the fibers, I guess would influence. So set time is measured by, we have these little needles, and we're measuring how much force it takes the needle to go down. So I think that the fibers in there would increase the tensile strength of the, the matrix.
Device. Okay.
Yeah, and right, I guess maybe so it'll take more pressure to push down through.
Okay.
But, yeah.
So the set time kind of is influenced a little bit by that, just being able to test what was going on.
Potentially, yeah.
There was a quick question here about you mentioned sandblasting is the best method for surface prep, but would there be any concern about why you're sandblasting a specific area blowing into another area, and how would we be able to do a larger area?
Right. Yeah. So I guess typically for new construction, doing an exposed aggregate finish using a paste retarder is preferred and I think gives the best performance, but for retrofit applications using the sandblasting. And right, I guess in terms of how to only influence the area that you want, I mean, I don't know specifically, but maybe you could use some type of shielding or
yeah. Probably very similar to paint. You know, when we're
right.
abrasive cleaning it for paint, you don't just do a specific area. It's a pretty large area. So,
right.
Well, with that, we can move on to the next presentation. So, thank you, David.
All right. Yep. Thank you, everyone.
Thank you, Paul and Rick. We're at the end of the second 40-minute module. Thanks again to David for presenting the second module.